Let's look at this problem that deals with a logistic function. So the logistic functions are special cases of exponential growth or decay where the capacity of the system limits the total amount. So you start off with exponential growth and then you reach carrying capacity. And so if we look at this function here, we have the number of cases over time, where time is measured in weeks, is 30,000 divided by 1 plus 20 e to the negative 2.0 t. The negative 2.0 t is the decay rate, the growth decay rate of the exponential part of the function. The 30,000 is the carrying capacity. If the time would go towards infinity, then that exponential would approach 0 and you'd get 30,000 divided by 1. So the most cases this system will produce is 30,000. The resources needed for more cases to exist would be the limiting factor here. But this question first asks, what is the number of cases at the beginning? And at the beginning is time equals 0. So let me come over to my blackboard here and bring this function across and we'll look at it. So we have the number of cases as a function of time is 30,000 divided by 1 plus 20 times e to the negative 2.0 t. And so the first part says, hey, what are the number of cases at the beginning? And at the beginning is when time equals 0. And noting when this is 0, we get e to the 0, and anything to the 0 is 1. So the number of cases at time equals 0 is 30,000 over 1 plus 20 times 1, or 30,000 divided by 21. If I run to my calculator here really quick, I get 1428 and some decimal places that we're going to round up to 1,429 people. Now, the second part of the question says, well, at 3 weeks, t equals 3, what are the number of cases? So if we substitute in, 3 times 2 is negative 6. And so we get 30,000 divided by 1 plus 20 e to the negative 6. Again, I have to run to the calculator here, making sure to put my parentheses to contain my denominator. And I get 28,582 and some change, which will round up to 28,583. Now, these type of logistic models are actually very common, realistic for things that happen very quickly, that are in an environment that has a carrying capacity, or the true long-term behavior of things when we look at a close scale appear to be exponential growth. But when they finally saturate their environment, the carrying capacity of the environment limits the growth. So these are important functions to play with.